So in the last lecture, we have finished with the example of Sn. Xn plus 1 belongs to Rn plus 1 such that summation of this is 1. Okay. Here. And the way we have constructed the charts in the example of S1, you can use the stereographic projection and we can provide a chart, coordinate charts for Sn also. Okay. So using stereographic projection, we can construct coordinate charts for Sn. In an analogous way, in the same way that we have defined for S1. And this proves that Sn is a topological n manifold. Topological n manifold. Okay. So this is true for any n greater or equal to 1. Now the next example is also an important one, because suppose you have an open set U, open set in Rn, and consider a continuous map F from U to another Euclidean space Rm. And with respect to this map, you can define the set which is called the graph of the function f, that is set of all those n plus m tuples, that is, it is in Rn cross Rm, where y is actually the image of x under f for all x belongs to U. So you can define this set, and so since this set is a subset of the Euclidean space R to the power n plus m, so you can impose the subspace topology on this graph of f. So this will be equipped with the subspace topology of R n plus m. Okay. Now you can define projection maps. Projections, that is pi n from Rn cross Rm to Rn by pi n xy equals to x. So this is going to be a continuous map And with respect to this map, if you restrict this pi to this graph of f, that is, if you define phi as the restriction of pi n to graph of f, so this is going to be a continuous map on yes, onto U, right, where its inverse is given by, so phi inverse of, suppose you you have considered one x, so this can be defined as x fx, right, x fx, okay, on the open set U. So then this phi inverse is a continuous map of U to Rn cross Rm. Okay. So therefore M phi, where M is the graph of f, is an appropriate coordinate chart for M, graph of x, f, sorry. Okay. That means the singleton set M phi is an atlas. Is an atlas for graph of f. So this proves that, so graph of f is a topological n manifold. Topological n manifold. Okay. As we have considered the open set U, which is lying inside Rn. So this says that this graph of f will be a topological n manifold. So consider any open set in Rn, and if you can define a continuous map from that open set to any other Euclidean space Rm, then you can easily construct a topological n manifold using the graph of the function f. So in this way, you can generate more and more examples of topological n manifolds. Okay. The next one is also okay. So the next example is also very important in the course of manifolds. In the discussion of algebraic topology in the discussion of projective geometry. So you will always have this example at your hand, that is, okay, so let me start with the space. Suppose that X is Rn plus 1 and it is punctured at 0. Okay. So then you can define a relation. So we define a relation. What is that? We define a relation on this punctured Euclidean space Rn plus 1. So what is the definition? So suppose you take two vectors x and y, the 2 points in Rn plus 1 minus 0. Then you say that x and y, x is equivalent to y if and only if there exists a scalar lambda. Scalar means it is in the field of reals. Okay, we are considering the scalar field as R here. So there exists a scalar lambda not equal to 0 such that x can be written as a scalar multiple of y. Okay, so x is equivalent to y means x is actually a scalar multiple of y. Okay, so it is your task to check that so check that this is an equivalence relation on Rn plus 1 minus 0. Now as you all know that an equivalence relation will partition the set Rn plus 1 minus 0 in terms of distinct equivalence classes. So we denote the set of all distinct equivalence classes as Rpn. It is a set of all distinct equivalence classes with respect to the relation defined above. Okay, this is the set of all distinct equivalence classes determined by the relation. This. Okay. Now, if you look at these classes, if you look at the relation at first, then you will see that actually, suppose if you draw a schematic picture of Rn plus 1, suppose it is your 0, or if you just think of the Euclidean plane, then suppose you have 1x, then what is the equivalence class of x? The equivalence class of x will give you a straight line passing through x and passing through the point 0. Okay, Lx, right? So for each equivalence class, you can associate a straight line Lx passing through the origin, and this straight line is unique for each x, right? If you take 2 points x and y, if x and y are distinct, then the straight lines determined by these 2 points passing through the origin, they are also different. So for each x belongs to Rn plus 1 minus 0, one can associate a straight line Lx passing through the origin and x, which is unique. So in view of this observation, you can think of RPN as the set of all straight lines passing through the origin 0. So you can think of RPN as the set of all straight lines passing through the origin. Okay, because you are having a one-on correspondence in between these two sets. The set of all distinct equivalence classes determined by the relation defined above, and the set of all straight lines passing through the origin. So you can think of this set as the set of all straight lines passing through the origin, right? So yeah, okay. Now if you come to the equivalence relation again, so for this equivalence relation, you will definitely have a natural projection, right? Natural projection, which is denoted as pi. So it is Rn plus 1 minus 0 to Rpn, because you have defined one equivalence relation on Rn plus 1 minus 0, and with respect to this relation, so for each point it will give you one class. So this is the natural projection from Rn plus 1 minus 0 to the set of all distinct equivalence classes determined by the relation. Okay, so this is your definition, that pi x goes to x class. Okay, and with respect to this map, we can induce a quotient topology. So we can induce a quotient topology on RPN, which makes the map pi a quotient map. And eventually it is continuous. So what is the definition of quotient map? What is the definition of a quotient map? देखो এটা ঠিক আছে okay so with respect to this topology So what is the topology induced on RPN with respect to this pi? That is a subset U of RPN is open. It is an open set if the inverse image of U with respect to the map pi is open in Rn plus 1 minus 0. So this is the definition of the topology with respect to this natural projection. And this is a quotient topology which makes this map a quotient map, right? Okay. So, okay. Now note that if V be an open set in Rn plus 1 minus 0, then pi inverse of pi of V, what is that? This will be the union of lambda V, sorry, the union of lambda V for all non-zero real number lambda. Okay, why it is so? I think I should leave this as an exercise. That pi inverse of pi V will be union of lambda V. Just use the definition of pi and the yes. Okay. So this decomposition of pi inverse of pi V tells you that so you are having a map x to lambda x, right, from Rn plus 1 minus 0 to Rn plus 1 minus 0. So this is a homeomorphism always, right? This is a homeomorphism for each lambda belongs to R minus 0 for all non-zero scalar lambda. And with respect to this observation, you can say that so this map tells you that so V, since V is an open set, so lambda V is also open. So this implies lambda V is open for each lambda belongs to R minus 0. Okay. And since pi inverse of pi V is the union of lambda V, the union of open sets, so it must be open. So this implies that pi inverse of pi V is open in Rn plus 1 minus 0, and this implies with respect to the definition of quotient topology that so pi V is open in RPN, and hence this pi is actually an open map. Okay, so the natural projection is an open map. Okay, so I think I should I think okay, so okay, so let us give you some aspects of aspects of those equivalence relations defined on a space X, okay, that makes the natural projection an open map. Okay, so that means, so suppose this be an equivalence relation. I'm just quickly revisiting the quotient topology and its beautiful properties related to this example RPN. So suppose this be an equivalence relation defined on a set. Suppose you are considering a set X. It is any set. I am not considering the RPN. So you are considering an equivalence relation defined on a set X. Okay, and with respect to this equivalence relation, you will definitely have the quotient set. Quotient set, that is the set of all distinct equivalence classes. Distinct equivalence classes determined by this relation on X. Okay. Okay. Now suppose I am imposing a topology on X. That is, now we are concentrating on a space X. That is, we are defining a topology on X. Okay. And with respect to the topology on X and the equivalence relation defined on X, we can define a topology on the quotient set. Okay, with respect to the natural projection map that we have already discussed in the example RPN. Okay, in the same way we can define this kind of things in any general discussion. Okay, so yeah, so define a topology on X like this via the natural projection. Okay, the natural projection map phi from X to the quotient set, this which is defined as yx goes to X class. Okay, and what would be the topology? The topology can be defined in the same way that we have already discussed for the case of RPN. That is, a subset U, subset of X. This quotient set is open if and only if phi inverse of U is open in X. Open in X. The same way we have defined in RPN. A subset U is open if phi inverse U is open in Rn plus 1 minus 0. And it is called the quotient topology Actually, this definition of open sets will give you a topology actually. Okay, that is a subset U is open. That is, if you define a tau such that U subset of X by this